everyone, I am Constantinou and I am currently working at Imperial College London, in which I also did my PhD. Today I will be presenting a project I've been working on the last years, and it was also the topic of my PhD thesis, on how to design thermoresponsive polymers and how I moved from my initial studies to making a polymer that is more suitable for the final application. So what are thermoresponsive polymers? Thermoresponsive polymers, which are also known as temperature responsive polymers, are polymers that they respond to temperature, and they do this by changing their solubility or compatibility with a solvent. The most famous thermoresponsive polymer in daily life is gelatin. So gelatin is a gel at low temperatures, for example in the fridge, while it's a liquid when you eat it, and this is because the temperature changes from room temperature or low temperature to body temperature. And once gelatin becomes liquid in your mouth, it releases all the nice flavors. So because gelatin is a gel at low temperatures and a solution at high temperatures, it's characterized as a polymer with upper critical solution temperature, or UCST. Polymers I've been working with, they have a property called lower critical solution temperature, or LCST, which is actually the opposite behavior. They are soluble at low temperatures and they are insoluble in a solvent as the temperature increases, and they do generally have a phase diagram like this. So as you can see here, at low temperatures it's a solution, transparent solution. When you heat it up, it becomes cloudy or even precipitates out of solution. All the data points here that they form this curve are the cloud points, while the lowest one is the lower critical solution temperature. If the polymer has the appropriate structure, it can form a gel, and normally what we observe is a phase diagram like this. So at low temperatures, regardless the concentration, we have a solution phase, so the polymer gets dissolved in the solvent. Then at low concentrations, when the solution is heated up, its phase separates. So you can clearly see in this picture that we have a solid polymer and the solvent on the top. Under the appropriate conditions, it can form a gel. So a gel is when you invert the tube, the sample does not flow, and this area here that is formed is called the gelation area. So it's all the temperature and concentration values that a stable gel is formed. So for example, here at low temperatures we have the polymer chains. They are free in solution. When it's heated up, these polymer chains come together and they form physical entanglements, and they trap the water molecules and they form a hydrogel, a 3D physical network. Thermoresponsive gels with lower critical solution temperature are extensively being studied as injectable gels. So the idea is that you dissolve the polymer at low temperatures in water, then you load it with either cells or drugs, mix it well, and then load it into a syringe. Upon injection into the body, it forms a 3D network that traps the cells or the drugs. This happens because of the temperature increase from room temperature to body temperature. In the case of drug delivery application, the network controls the slow release of the drug to the surrounding environment, and this is useful because you have a more targeted release rather than a systemic release of the drug. In case of the cell incorporation, it's very useful in tissue engineering applications, and ideally you want the cells to form a new tissue at the same rate as the network dissolves and gets removed from the body. The most recent application of thermoresponsive gels with LCST is 3D printing, and when the printed structure is used in bio applications, then the thermoresponsive gel is useful for 3D bioprinting as well. So in the case of 3D bioprinting, thermoresponsive gels are mostly used as sacrificial materials. To explain this further, So you have the thermoresponsive gel. It's a solution at low temperatures. You easily load it into a syringe, and then you heat up the syringe at the temperature of the printing, which is higher than the gelation temperature of the thermoresponsive gel, and you print the structure while being in the gel phase, and this is possible because of the shear thinning properties of the gel. So in this case, you print a sacrificial mold, and you fill this sacrificial mold with the material in interest, which is followed by curing. So for example, you could apply UV to cure the material in interest. Then you lower the temperature of the mold and the scaffold below the gelation temperature of the thermoresponsive gel, so the gel becomes solution and it washes out of the scaffold by letting behind pores that are useful, for example, in tissue engineering, because they allow nutrients to pass through. So the most extensively used thermoresponsive polymer belongs to the family of Poloxamers, and it is also commercially available. It is known as Pyrronic, sometimes Imperial and Anterox, depending on the company, and is extensively being used as a detergent or a gelling agent. The member of this family that is a thermoresponsive gel is Poloxamer P407 or Pyrronic 127. And this polymer, when dissolved in aqueous media, it forms a gel at concentrations of at least 15 weight%. So the idea is that we have to try and find something that forms a gel at lower concentrations than 15 weight%, which will be very cost effective for the final application. So the aim of my project was to establish structure-property relationships. I was changing the polymer structure, and I was interested to see how this change will affect the final properties. So in terms of the structure, in nature, each specific protein every time is formed, it has the same length, same composition. However, in the lab, we always end up with distribution of different polymer chains with different molar mass or different composition, and ideally we want these polymer chains to be as similar as possible. So after the synthesis, I confirmed the molar mass characteristics with gel permeation chromatography or GPC, and the composition with proton nuclear magnetic resonance spectroscopy, NMR. So in our lab we are using a technique that is mostly known in industry called group transfer polymerization or GTP. This technique is anionic polymerization, so the polymerization goes through anions. It is very fast, 15 minutes per block, and here I'm just giving an example of diblock polymer synthesis. We have the flask, we are adding firstly the catalyst, which is going to activate the reaction, then the initiator, and then we're adding the first monomer. We're forming the first block short polymer chain in maximum 15 minutes, and then we're adding the second block, and in half an hour we have a diblock polymer. GTP is very useful because it's very easy to scale up to industrial scale if needed. Then it's performed at room temperature, so we don't need to spend energy on making the polymers, and it produces well-defined polymers, so polymers with low dispersity values, normally below 1.2 depending on the architecture and the monomer. After synthesizing the polymers, I was dissolving them in water in order to investigate the self-assembly and thermoresponsive behavior. So in terms of thermoresponsive behavior, for example here, this polymer solution is soluble at low temperatures. When it's heated up, it forms a transparent gel. Then depending on the gel, it might become cloudy upon further temperature increase. So the self-assembly is investigated by dynamic light scattering, and then through visual tests constructed phase diagrams to show at which temperature and concentration values the polymer is soluble or insoluble in water, and to also show the gelation area, so the temperature and concentration values at which a stable gel is formed. The gelation was also confirmed by rheology, which also showed the strength of the gel. For the polymer synthesis, I used methacrylate monomers, either commercially available or monomers that we synthesized in the lab, and we carried systematic studies. So I changed the structure and I wanted to see how this will affect the property. But for example, if I wanted to investigate the effect of architecture, then all the other parameters were kept constant. For example, the molar mass and the composition was kept constant and only the architecture was varied, and so on. To design thermoresponsive gels, you want to incorporate different type of units. Of course, you want the thermoresponsive unit, which is the one that will promote gelation. You need the hydrophobic unit, which is the one that avoids interactions with water, and this is to promote self-assembly, and also a hydrophilic unit to balance the hydrophilicity of the structure. So in the example given, blue is hydrophilic, red is hydrophobic, and green is thermoresponsive. When you dissolve this in water, it will form a micelle, like is shown in the structure here, with the core being formed by the hydrophobic block, because this block avoids interaction with water, while in the corona of the micelle we have the thermoresponsive and hydrophilic units. Many studies that we've published are based on amine monomers. So for example, here we have a polyethylene glycol methyl ether methacrylate, or PECMA, of various lengths, so we can have different length of side chain. Then a commonly used in our studies hydrophobic unit is butyl methacrylate, and the thermoresponsive unit in most of our studies was 2-dimethylamino ethyl methacrylate, or DMA-EMA, which is also pH responsive. So in the previous studies, what we investigated was the effect of architecture. For example, we varied the position of the block from ABC to ACB or BAC, and it was proven that the ABC architecture was the best. The other one, the parameter investigated was the molar mass, and it was proven that molar mass around 10 kilodalton is ideal because it forms a gel but also ensures solubility. And in terms of composition, it's best if the hydrophobic content is kept around 30%. So in one of my first studies, I wanted to expand the type of architecture studied. So I've investigated the common ABC, ACB, BAC triblocked polymers, but also diblocked polymers. For example, P4 to P6 is the novelty of this study. As you can see, for example, in P4, you have a first block that is a random copolymer of the hydrophobic and hydrophilic units, while the second block is the thermoresponsive block, and so on. In this study, it was proven that the ABC architecture is still the best, so it confirmed the previous results. Then one of the latest studies of the group was on thermoresponsive tetrablocked polymers, and this is actually the first systematic study on this subject. And the molar mass and composition were kept constant, and the only thing that changed was the architecture to have a systematic study. So for example, polymer 1, 2, 3, they have 2 A blocks, so 2 PECMA blocks, hydrophilic ones, different combinations. Then polymer 4 to polymer 6, they have 2 hydrophobic blocks, while polymer 7 to polymer 9, they have 2 thermoresponsive blocks. A triblocked polymer was also synthesized for comparison, and what's important to mention here is that more than 20 grams of each polymer was synthesized, and all these polymers were synthesized on the same day, and that's where GTP is useful for, because it's very quick, so it allowed the synthesis of all the polymers on one day. So in this study, depending on the different architecture, we have a different self-assembly. So for example, we can either have the traditional core shell micelles, or these here are flower-like micelles because you can see that the polymer chain bends to form the micelle, and it was actually proven that the different architecture controls the self-assembly, and it also controls the gelation. And it was proven that polymer 9 that forms the smallest micelles showed the best gelation properties with a very wide gelation area. So our latest study was based on a different amine based monomer. In this case is diethyl amino instead of dimethyl amino. The difference is that this monomer is of course pH responsive because of the nitrogen, but it also has tunable hydrophobicity. So depending on the pH, if the pH is low, it will be protonated, so hydrophilic. If the pH is high, it will be hydrophobic. So in this study, it was actually proven that at low pH, where the amino groups are protonated, the thermoresponse is disrupted. So even if you heat it up, it will remain at the solution, while at alkaline pH or in PBS, where the amino groups are in the neutral state, then when increasing temperature, you will get the formation of a gel. So in the current studies that we are working on, we are trying to move away from the amine monomers because they might induce toxicity, cell toxicity. So we are making polymers with these monomers here. So we're using either ethylene glycol based monomers or propylene glycol based monomers, and different alkyl methacrylate monomers such as butyl methacrylate. We have recently developed a polymer that forms a gel at very low concentrations, and here I present the phase diagram of it. So in transparent, we denote the runny solution phase. In red, you have viscous solution phase. In blue, it's stable gel, so when you invert the tube, there is no flow detected. And in green, we have two phases, so either gel syneresis or precipitation. And you can see this here on the pictures. So a transparent solution, when you invert the tube, it does flow. A stable gel, that it can be either transparent or cloudy depending on the temperature. And gel syneresis or precipitation, as you can see here, we have the solids and the liquid that it did flow. So in the case of our polymer, as you can see, it has a very wide gelation area, and it forms gel at even 2 weight percent and at body temperature at 5 weight percent. To remind you, Pyronic, which is the commercially available thermoresponsive polymer, it forms gels at 15 weight percent and above, and you can see that our polymer outperforms Pyronic in terms of gelation concentration, and it actually forms gel at body temperatures at 3 times lower concentration than Pyronic. So the gelation was also confirmed by Rheology at 15%. This is the result here. For those who are not familiar with Rheology, when the storage modulus, here shown in blue, is higher than the loss modulus, then you have a gel phase because the material is able to store energy, while when the loss modulus is higher than the storage modulus, then it's liquid because the material loses energy. So as you can see here, at room temperature, the loss modulus is higher than the storage modulus, so it's a liquid, while when the temperature is increased, they both increase in magnitude, and eventually the storage modulus, so the blue, is higher than the loss modulus, and it is where we have the gel formation, and this is followed by gel syneresis and precipitation, which is indicated here because the two moduli cross again. So to conclude, our group is expert on using group transfer polymerization, which is a quick and easy technique, and we are carrying out systematic studies on thermoresponsive gels. We vary the architecture and the composition, and we have proven in several cases that it controls the micelle formation and micelle size, and it therefore controls the gelation. Our best performing polymer it outperforms Pyrrhonic F127 in terms of gelation concentration, so it has a great potential to be used in different applications, including injectable gels or 3D bioprinting. So recently I'm also working on a different project on antibacterial membranes. So this project involves the synthesis of polymers with antibacterial properties. Then these polymers are used to fabricate polymeric membranes, which will have antibacterial properties, and the final idea is to evaluate these properties. I would like to acknowledge the Department of Materials of Imperial College London for funding my PhD studies, and part of this work that has been presented today, it was for my PhD. Then I also would like to acknowledge EPSRC for the Doctoral Prize Fellowship that I have been awarded and did after my PhD, and I'm currently funded by Leverhulme Trust on the project working on antibacterial membranes. And I would also like to thank Theoni's group, and especially Theoni Georgiou, for her assistance and guidance all these years. And thank you all very much for your attention.